Good afternoon, everyone. For the second last time, I am very happy to see you. And as it is the start of another week, we do have our historical figure. Now, I know normally there's some exciting little demo. Stay tuned for tomorrow for our very last class. So this is Richard M. Karp, also known as Dick, and he is one of a number of great Jewish American computer scientists. In this case, he is a computational theorist and a complexity theorist, and this is some of what we'll talk about in the remaining time allotted to us. How to actually step back and understand algorithms from a really, really big picture. He was born in 1935 and now works at UC Berkeley, where he received the Turing Award for studying the fundamental nature of computation. So I've talked a few times about what is the largest computation one could do, what are the scaling laws that underpin algorithms in general, and he was one of the father figures in this particular area. He was also responsible for the development of the notion of polynomial time, which really sums up large numbers of practical algorithms that we use, and we'll discuss this a little more, as well as the idea of NP completeness, which is one of our big capstone exciting but non-assessed topics remaining in the class. So what now? We seem to have learnt a whole bunch of different algorithms. We've learned a whole bunch of different data structures, and we do have a few different options for what we could spend our remaining time on. Now, unfortunately, I've chosen for you, but one option, we could just take a look back at all the algorithms that are out there, at all the algorithms we've done, and start to categorize them and understand into what different groups they fall. So to try and draw some conclusions about what can we tell about algorithms from everything that we have learned so far. So we could group our algorithms by problem type, is it an optimization problem? Is it a problem from physics? Is it a numerical problem? What kind of problem is it? We could group by complexity class. So we've talked a little bit about this. So all of the O of n algorithms might be in one class together. All of the n log n algorithms might be together. Or we could categorize them by design technique. So we talked a little bit about some design techniques earlier, and we'll explore each of these three options a little bit. So first, what about problem types? So here I just went to Wikipedia, and I went to the big list of algorithms. And you can see there are planning algorithms, combinatorial algorithms, sequence algorithms. And so this is one option, and it is actually a useful thing to do from a practical perspective, because after all, we are computer scientists trying to solve certain types of engineering problems in the real world, and we might want to go ahead and find optimal algorithms to solve our individual problems. So among some of them might be modeling animal behavior, filling in blanks in damaged family photos, which is something I've played around with at home recently just for fun. Algorithms that can find other algorithms or can find mathematical proofs for us. This is a big, exciting area of research. Determining optimal train routes. There are a whole bunch of really cool things that you can now do as a result of having learned the general structure of how one writes an algorithm. Now, you might not be able to design the algorithm from scratch off the top of your head, but you should now at least feel a little more empowered to go out there and look at algorithms and understand them and try and piece together how they work. Another thing we can do is jump up one level of abstraction and try and think about the different techniques by which one could actually design an algorithm. And we'll spend a little bit of time on that point. So among the different types of algorithms that we'll look at, I've shown a bunch on the board. Let's start with generate and test, which is probably the simplest form of algorithm that we could come up with. So what are some examples of an algorithm where you might just try and generate solutions and then test them after the fact to see if you've generated a correct solution? And Toby, you haven't spoken much in a little while, so you get to start off today.
Well, I guess sorting algorithm. Sorting.
Sorting? So do you think that's a good way to sort things? To generate a random ordering of the items and see if it's sorted?
Okay, if it's generating random.
Generate and test is where we try and guess a solution, and then we check if our solution was right. So for string search, that would be guess a random index, and then check if you've guessed the correct index. So it seems like this is kind of a weird sort of algorithm to use for things like that. Another example that you might have heard of just colloquially is the monkeys on a typewriter generate and test. So you have your monkeys, it generates some text, you look at the text, is that Shakespeare? No? Okay, monkeys, go and generate some more text. Is it Shakespeare? Nope, nope, nope. And this is one of the problems with generate and test is you might be generating the wrong thing a whole lot. So let's look at one type of problem for which we don't really know algorithms that are that much better than generate and test. So generate and test will at least give us a reasonable first approximation to the best algorithm. So this is the problem called subset sum, and this is one that's actually quite important, so I'd want you to know it for any future assessment. And it's a specialized version of what we call the knapsack problem. So who here has a small bag and a lot of things that they generally want to fit in their bag? Okay, Blake. So Toby, get that microphone back to Blake as fast as possible.
Testing, yeah.
And Blake, could you explain your problem to us that you've been having with your backpack?
Well, I need to bring my maths folder in every day. I need to bring my laptop as well as lunch, and a drink bottle and pencil case and stuff.
And so what's the challenge for you, given a whole lot of items in your backpack?
I got to try and fit them in and bring them all.
And assuming that there's not room to fit everything, what do you do?
Well, some stuff I have to leave behind or maybe change around the order of where they're placed.
Yep, so at the end of the day, we've got a backpack with a certain capacity, and assuming that this is a very magical backpack that can model itself to whatever shape the items are, but it still has a fixed capacity, our job is going to be to pick the items such that we've optimally matched the backpack's weight. Now, we could do this in two ways. We could try and get as close as possible to the capacity of the backpack, or we could ask ourselves a decision problem. Is it possible to select a subset of items such that we have perfectly filled out our backpack or our knapsack? More mathematically, given a set of integers s and a target t, is there a subset of the integers that we can combine such that when we add them together, we get exactly t? So our analog here would be each of the numbers would be the volume of the item, and the target would be the volume of the backpack. And so we want to find, is there a subset of items that perfectly gets us to the exact volume of the backpack, allowing Blake to go about his day in peace. Now, this is an interesting sort of algorithm because we're looking at the decision problem. It's just a yes or no question. For this specific type of algorithm, and we'll talk about why I care about it in a minute, all I want to know is not which of the items, but is there a set of items? And this becomes important not for practical purposes in our algorithm, but because it's going to be a tool that we use to do proofs further on, and that will actually teach us about the nature of the algorithms. So I've got three versions of the problem. An optimization one, how close can you get to the volume of the backpack? Another version of the problem, which is can you get there exactly and which items do you need to pick? And then a final version, which is just the decision problem. So is there a subset of items that will get you to exactly t? Now, for the time being, let's just jump right to the code and see how one might implement this in a generate and test fashion. Jack, you want to? Blake, pass the microphone back to Jack.
Is there any, I guess, restrictions in what should be adding up? Like, I don't know, in the backpack example, a bunch of things might combine to reach the volume, but you've left out something important like a laptop.
So in this version of the problem, we're simplifying that away. It's okay if Blake packs 50 bananas and no laptop. In the real world, obviously, we'd need to design our problem a little differently. We might only need 5 bananas and 1 laptop, which is more or less what I take to work every day. I'm being dead serious. I pack a lot of bananas to work.
I'm concerned for your potassium levels.
Okay, so this is our subset sum implemented in code, and it's going to be important for us later, as well as for understanding the generate and test strategy. So here is our sample data, and what we're going to do is we'll allow the user just to feed in the parameters of the target that they want and how many items they want to choose from, just to allow us to test different versions of the program. Then what we do is we're going to print out the values and we're going to run our subset sum function. So up until this point, it's all just the normal kind of setup-y code that we're used to seeing so many times in semester. Now, the subset sum algorithm that we're going to present, our generate and test algorithm, is really, really simple. It's a basic recursive algorithm that each time is going to figure out what the new target is had we included this item. So let's say our laptop weighs 50 kilos and we have, not weighs 50 kilos, there's a volume of 50 centimeters squared, or whatever it happens to be, 50. We're going to throw out units. I'm not a physicist anymore. It's 50. And we have an available volume to us of 100. If we choose to include the laptop, then we have 50 remaining. So in our recursive call, we're going to look at two possible options. Either we include the laptop and we're now at 50 left, or we don't include the laptop and we're still at 100. And so that's going to be our two recursive calls here. So we have one recursive call, which checks to see, is this possible to do if we have included that laptop? And the way we do that is by reducing the target, here k instead of t, by the volume of that item. And the volume of the item is just what we fished out of the array. So assuming we're checking to see if we're going to insert the nth item or not, the -1 is again, remember, because of the way that array indices work. So this is the case where we have chosen to include the item, and this is the case where we have excluded the item. Then we have a base case where we have successfully, where there is no room left in the backpack whatsoever. So if there is no room left in the backpack, that means we have packed it perfectly. Or in the other case where there is, there's the case where we have packed the backpack perfectly because our target is equal to 0. Otherwise, if there are no items left to choose from, but there is still room in our backpack, then we have failed. We haven't exactly filled out the backpack, and there are no possible items left for us to choose from. So our basic strategy here is try all the different combinations. Try the combination where you include the laptop, and then all the recursive versions where the laptop is included. Try a version where you don't include the laptop, and then try all the versions where that laptop is not included. And that's pretty much it. So let's give that one a run. And we can see that with 20 items selected and with a target of 1,000, we're successful. So now let's just try it with different settings. Let's try 5 and 300. In that case, it failed. So this is an example of the decision version of the problem where our goal is just to know, is it possible to choose the subset of items such that we get the correct answer? So what was your name again? It had 2 Ks in it, Kok Fung, right? I didn't get it quite right. Say it once more for me. Kok Feng. That's it. I'll get it one more time from you later. So let's get the microphone all the way back there. So our goal here is to figure out what is the runtime of this kind of algorithm. So let's say we have one item to choose from and a target of 50. How many possible options are there?
50.
Well, we've got a volume of 50, but we only have one item to choose from. How many different ways could we choose to include this item or not include this item?
Just one.
Well, there's the version where we include it, and there's the version where we exclude it. So we've really got 2. Now let's say we have 2 items. How many combinations are there of including and excluding?
4.
4. And if I have 3 items?
9.
Is it 9?
6, maybe.
2. So there are 2 versions for 2 items. There are 4 versions for, 2 versions for 1 item, 4 versions for 2 items. So every time we add an item, we take the prior number of combinations that there were, and then for each one of those, there are 2 more versions. There's one where we include the new item and one where we exclude the new item. So if we had 4 before and we multiply that by 2, what do we get?
8.
So if I do it again, now I have 4 items.
16.
And what's this pattern? If I have n items, what is the formula that gives me how many different combinations there are?
2n.
2 to the n. So that is our runtime here. However, once we've chosen the items, what do? We have to do one more step before we know if these are the right items or not.
You check if the items completely fill the space.
Yeah, and the way we do that is by summing the values of the items together and determining what they sum up to. Do they sum up to the right amount? And let's say that addition takes O of 1, just takes one step, and we have n items. How many steps do we have? It's an easy question.
1.
Well, we don't just have one step because we've got to do n additions, right? So it's O of
N.
O of n. So 2 to the n combinations, and for each combination, how much work do we do? You just said it.
1.
No, not 1.
Sorry, can you repeat the question?
So let's say we've picked a combination of n items, and we have 2 to the n of these. How much work do we do for each combination? We have to do this summing thing, right? So how much work was that?
O of N.
O of n. So our final thing, multiplying it all together, 2 to the n combinations multiplied by n work for each combination gives us a total runtime for our generate and test algorithm of 2 to the n multiplied by n. Now this is pretty bad, right? This grows really, really, really quickly, or even on one of our normal computers, by the time we get to a couple of hundred items, that is going to be well outside the capacity of any ordinary computer or even a supercomputer to run. And even with fancier algorithmic techniques, we're not going to get much better than 2 to the 0.291 n, which is still kind of like 2 to the n. So not quite, but it's still really, really bad. So subset sum, at least by the algorithms we know today, is really difficult. Okay, new problem. What is this? Sudoku, yeah. So for the rest of the semester, all we're doing is Sudoku. So everyone get out your pen and paper. Okay. Kok Feng, do you want to pass it? Not Alistair, the guy in front, whose name I don't know. Yeah. What's your name?
Avikna?
Avikna. That's right. Sorry, it's been a while.
Sorry.
Tell me how this works, for those who don't know.
You have to get all numbers between 1 and 9 in a square, and I think along a line as well.
Yeah, so we've got a couple of different rules here. It's a game, and what I'm going to challenge you to do is a decision version of the game. So does this Sudoku have a solution? And so we have a 9 by 9 grid, and there are 9 possibilities for each square in the grid, and a possibility is a number from 1 to 9. And as Avikna said, we have some rules that determine whether a given filling of the grid is valid or not. So for a given 3 by 3 subgrid, it has to have all the numbers from 1 to 9. For every row, it has to have all the numbers from 1 to 9, and every column has to have all the numbers from 1 to 9. So naively, if we have a 9 by 9 grid and 9 possibilities for each cell, how many solutions are there for us to generate and test?
Is that 81?
Only 81 for every Sudoku? 81 in total?
No.
So how many squares are there?
81.
And how many options are there for each cell?
9.
So what's our computation?
9 times 81.
9 times 81?
9 to the power of 81.
9 to the power of 81 possibilities. Now this is a pretty astonishingly large number. Let's simplify it down to powers of 10. So this is 10 to the 21, which is still really, really large. It's about 3 centuries to test every possibility for a Sudoku. Now, probably not great. Now, there are a bunch of papers that have actually researched Sudoku. It turns out it's a super fun problem for computer scientists because it's fairly easy to define what the problem is. And so one question that you might ask is, what makes a Sudoku solvable? And computer scientists have found that the minimum number of clues you need in order to make a Sudoku have a unique solution is 17. So they performed an exhaustive search for 16 clue puzzles and didn't find any, proving that the answer is 17 because they found one at 17. So just kind of a fun thing. But obviously, exhaustive search is not really going to be the way to go. Generate and test purely is going to be a little rough. So one question for us is, can we shrink the number of options that we have to test? Are we going to test all 9 to the 81 solutions? No, Rex says no. Rex, how do you solve a Sudoku? Avicna, do you want to pass down the microphone, and then we'll hear from Isaac in a minute.
When testing Sudokus, anytime you see 2 of the same number in a row or a square or a column, you can immediately scrap it.
So what is the technique that you use? If you had to describe the technique that you're doing at a high level.
Um,
A 3-year-old comes and says, how do you solve a Sudoku?
so I start by looking at the number 1, and then I look at if there's a 1 in every box.
Yeah, but what would you call that? Call this process that you're doing?
Scanning, maybe.
Scanning, or is there a form of reasoning you're using?
Well, I'm not
Probably
sure.
logic, right?
Right,
You're doing deductive reasoning.
Yep.
So you are seeing what clues are available and what inferences you can make based on those clues, and using that to narrow down the set of possibilities that you're actually testing. Now we'll hear from Isaac, who has a question.
Yeah, I was just going to ask about that paper, the 16 one. How can they say that they're not solvable? Like, what's their limit of logic?
So you'll have to read the paper for that. It's been a little while since I've read it, but they checked every possible 16-clue Sudoku to see whether it was solvable by logical inference from those clues alone.
Okay, cool.
So we have a couple of ways that we could approach our Sudoku. So the first is we just use a pure generate and test solution that would look something like this. Now this is just very sketchy pseudocode. Don't actually try and implement this the way I've written it, because A, it's not in a real programming language, and B, it's quite possible there's a bug somewhere. But our general strategy would be for any given grid, pick an empty square, fill the empty square, and see if filling that empty square the way you have chosen to fill it leads to a valid solution. And the way you do that is call that function recursively again. So say you put the number 1 in the top left hand. Look at all the different possible outcomes that would result from you putting a number 1 in that corner recursively. And then if one of those returns true, then you know that this leads to a valid solution, and therefore the overall Sudoku has a valid solution. On the other hand, if the number 1 doesn't lead to a valid solution, try it with a number 2, and look at all the possible game boards that have a number 2 in the top left corner. And every time you find a solution that doesn't work, backtrack up to the point where you entered a wrong number, and then try all the right numbers again. And when Rex is actually doing one of these puzzles, this is probably a strategy that he uses some of the time when there's not a clear single solution. So where you have a clue that might be ambiguous, one thing you might do is you might say, oh, this could be either a 2 or a 9. I'm going to try it with a 2 and then see what outcome that gives me and try and solve the puzzle that way. And if that fails, then you go all the way back and you say, well, it must have been a 9 then. And then you try and do it with all the ways that this would have gotten to a 9. So that's what solving it looks like using this strategy. And that's perfectly valid. And it can be one form of logical deduction. But we probably want to do a little better than that, because using that as the only strategy is going to give us way too many solutions. So our other strategy is going to be what we'll call constraint satisfaction and inference. Constraint satisfaction is a class of problems where we have a given set of rules about the state of the world that we want to see, and our task is to find a way to satisfy all of those rules that we're being told. So just like in the Sudoku, you're told, well, only one number per box, and that number has to be 1 to 9, and every row has to have the numbers 1 to 9, each appearing only once. So each of those are constraints, and we're trying to satisfy all those constraints simultaneously. And there are lots of different examples of constraint satisfaction problems in life, and in computer science, and in games. And this is the class of problems that you might look at, and now you know the keyword if you want to look it up. Another, who's got the microphone right now? Isaac, you have it. Do you want to pass it to Hania for a second? That was your name, right? No? Yeah. Nabia. Got Nabia, Hania, and Rania, and I sometimes mix all three of you up. Okay, so what is an example of a constraint satisfaction problem that you have every semester? At the start of semester before classes begin?
Sorry,
Okay, so the answer is going to be when we're doing timetabling, right? When you're picking your subjects and you're looking at your week and you say, okay, I can only have one subject happening at once. I know I have work on Thursdays, so I can't put any subject on a Thursday. And I know that I have to take at least either one of Calc 1 or linear algebra. And so you get this complex constraint satisfaction problem, and that goes as well with like scheduling lecture theatres. So these types of problems are really everywhere. And so the next trick is figuring out good ways of tackling these problems. So it turns out that there is a really beautiful way of representing a Sudoku as what we call a satisfiability problem, or a SAT problem, which makes really explicit these constraints. And I was revisiting the paper this morning. It's super fun. And one of the reasons it's interesting is because satisfiability is really a classic example of a good computer science problem. So let's try and look a little bit into how we'd write out these constraints explicitly and then try and use logical deduction. And for actually the techniques of deduction that we'll use, you'll have to either go and solve the Sudoku yourself or to take a higher class. So let's say we have a grid of that's defined by 3 coordinates: the x-coordinate, the y-coordinate, and the coordinate of what number is present in a given box. So S00 will refer to the top right-hand corner, and then the last index will refer to what number is set. So for example, we can see that S009, there is a 9 in the top right-hand corner, so the variable S009 is set to 1. That means that S001, S002, S003, all the way up to 8 are all set to 0, because the only number that's appearing in that corner is a 9, so the variables that represent all the other numbers that could appear in that box are 0. They're set to false. Now let's look at another example. So at row 0, column 1, the number 8 appears, which means S018 is set to 1. And then in that bottom corner, we have index 22. And so 22 is set to 6, which means that 226 is set to 1. And there are a whole lot of other zeros in our problem. Is that a question, Jack? Yeah, so I'm going 0 is the top left-hand corner and 22 is the bottom. Top right-hand corner from your perspective is 0, 0, bottom left is 22. And of course, we could expand this coordinate grid to our entire set of 81 squares, so they'd range from 0 to 8 and 0 to 8 on the rows and columns respectively. Which means we can write out this whole thing as a big logical statement. Now, just to give you some notation, this the wedge that we'll call it, which is like the triangle, is going to mean and an upside down wedge like a V means or. And when you say and, it means that both of these things are true. So in this case, it is true that S001 is 0 because there isn't a 1 in that top right-hand corner. And it's also the case that S002 is 0 because there is no 2 in that corner. And let's go all the way along there until we get to S009 is 1. So it is the case that the number in the top right corner is a 1. And now we have to add another and do that for the next square, and the next square, and the next square. And we would have one of these lines for every one of those 9 squares. And I've only shown 3 of them here because it would take me an awful long time to write out. So the next thing we might try do is write out some OR statements and see for which of the assignments is this particular constraint true. And that's essentially the question we're asking. Which of these values is true? Is it the case that the number appearing at 02 is a 1? Or is it the case that the number appearing in 02 is a 5, or a 7, or an 8? And what we want to do is find a setting of these variables such that this statement is true, and this statement is only going to be true where one of the variables is. So we could put together a whole lot of constraints to represent our entire Sudoku. So here is a set of some of the constraints that we want, and this is going to be unassessed. So you do not need to know how to solve a Sudoku using the constraints. It's here kind of for fun. So the first set we'll have is for all the values of y and x, and it must be the case that there is at least one number in every cell. So it must be the case here that every cell does have one of those values set to true. That's saying that at least one of those values are true. I haven't found a way using my constraint yet to say that at most one of them are true. We'll get to that point though. So there is at least one number in each cell. The next constraint is each number appears at most once in each row. And the way I'm doing that is just by having a statement that includes nots. That funny little bar symbol means not. So this means it is either the case that what you're looking at is false in one location, or it's the case that something you're looking at in another location is false. And by pairing this up multiple times and saying, okay, it's either one of these that can be set to true, or it's one of these that can be set to true, or it's one of these that can be set to true, etc. And doing that in the right combination, you can start enforcing more of the constraints. And I'm not going to go through the whole thing because it would take a very long time to try and explain the intuition behind it. But again, not important. The main thing here is to recognize that we can do this. Now, unfortunately, these constraints aren't enough. And these are already a lot of constraints, right? This isn't one. This is like lots of constraints for 9 times 9 times 9 constraints for that one, and then 9 times 9 times 8 times 9 constraints in that one, and then 9 times 9 times 8 times, a lot of constraints. But we're not done. We also need a constraint to say that each number 0 to 9 appears at least once in each 3 by 3 grid. So Sudoku has a lot of different constraints for us to satisfy. And then at most one number per cell, each number at least once in each row, each number at least once in each column, and then each number 0 to 9 appears in each 3 by 3 grid. So does anyone have a rough guess? I mean, I guess, Finn, you've got the microphone. How many clauses do I have altogether?
How many clauses?
How many clauses altogether? Once I've done all these multiplications and added it all up, what do you think?
Millions, maybe?
So not that big, actually. It's only about 12,000 clauses. So Rex, when you're solving a Sudoku, is this the path you use? Nah. So humans are actually pretty good at picking out which of the clauses are going to be most relevant. But kind of what you do when you're scanning through the grid is you're looking for constraints that are very nearly satisfied such that you can make a direct inference. So really what you're doing is you're picking out of all of these different constraints the one that seems most relevant. And there are ways to optimize this in a computer. So even if we have a large number of clauses, we can have a systematic process for figuring out which clause will actually give us some information very directly. However, at the end of the day, this is still fundamentally a hard problem because unless we have enough information such that it's very deterministic, this kind of problem, this satisfiability problem, does not have a general algorithm that can solve every instance of it. In Sudoku, the puzzles that we get are very specially designed such that it doesn't take you many clues, such that it takes you like 17 clues, and then you have enough information to actually solve the puzzle. For real-world instances of satisfiability, that is not always going to be the case. So what are some of the limitations that we've learned about generate and test? And do you want to pass up one row behind you? Yeah. Remind me your name over there.
Aiden.
Aiden. Okay, so what are some limitations of the approach that we've been trying thus far?
It requires like a decent amount of like memory, I suppose.
Lots of memory? What else lots of?
It might take a lot of time, I guess.
A lot of time. So there are ways, again, to do these time-memory trade-offs. So a lot of the time, we can just generate a solution once and then throw it away and generate another solution. So we might not have memory constraints, but the solution space might be really big. We'll have way too many possible things to generate and test. This is like in a chess game, which player is going to win, assuming they have the starting move. We don't actually know the answer. Is it that white really has the advantage, or is it that black really has the advantage? We're not able to generate every possible chessboard to see, okay, if black was playing optimally, would they always win, or if white was playing optimally, they'd always win. Just for reference, it is generally believed that white has an advantage, but we don't actually know for sure. There are also cases where we might not know how to generate the example solutions. In the things we've seen so far, it's very clear how to generate the space of possible solutions, but that's not true for every different algorithm. It also might be hard to explore the solution space fairly in a way that gives equal weight to every different solution. And then finally, it might be slow to do this generation process compared to just constructing it. And that's kind of what we had in our very narrowly constrained Sudoku. We could construct it directly from more concrete pieces of information rather than just randomly generating. So that's our generate and test strategy, and we'll come back to Sudoku a little later in our exploration because it still has a bit more to give us. Our next strategy is divide and conquer. Now, Aidan, do you remember one of our divide and conquer algorithms we talked about, I think, last week?
Sort merge?
Yeah, merge sort. That was a really good one. So the idea here was that we take a problem that we don't know how to solve on the full set of data, but if we keep dividing it and dividing it and dividing it into smaller problems, eventually we get to a problem that we do know how to solve. We know how to sort one item, we know how to sort two items, and then the only challenge for us is to figure out how to put our smaller solutions back together. And we can do that in a bunch of different ways. So we could do that with binary search, where we made our search space smaller and smaller and smaller and smaller until we came to an example that we knew how to solve easier. And then quicksort, again, same kind of view. There are some gradations and some shades of gray in exactly how the divide and conquering was working. But also our longest common prefix was another example of this where we could divide up our array into smaller subsearch problems. So that was our divide and conquer tactic. We've seen it a whole bunch during semester, so we're not going to talk too much more about it now. One that we are going to spend a little bit of time on, though, is simulation and randomization. And let's pass the microphone back once more again, and we'll leave it there for the minute. So you'll have it for a second. I don't have a question for you just yet, so you can keep sleeping, or try not to sleep too much. 5 minutes. So my research actually overlaps with some of this area. The idea behind simulation is you try and construct a computerized model of the thing that you're actually studying. So for example, that might be a physics system. We have a couple of physicists in the room. Put up your hand if you're doing physics. No one here today? Oh, all our physicists are busy. Rithik? There we go. So our physicists are busy in this kind of task, and perhaps that's why we don't have so many here today. But let's say you are trying to do particle collider physics, and you want to know what would happen if I built my particle collider this way with this much energy around it. Speeding up my particles to this speed, would it work? What you might do is you might write down the physical laws as equations inside your computer and then start to do simulations about what would happen to, say, your meter that measures the energy of a given particle if the energy of the particle exceeded a specific threshold. And so you'd write in your laws, and then you'd generate a whole bunch of different scenarios using random numbers. And this is what a lot of my research is focused on, is this random number generation process. And surprisingly, you can often use random number generators to solve problems that don't seem like they have randomness in them at the beginning. And this is going to be a little mysterious and a little cool, so I will turn us over to a video for a minute. leveraging what we know about the ratio between the area of a circle and the area of a square in which it's inscribed, we can actually compute the digits of pi by generating points within the square and seeing what proportion of them fall in the circle, as opposed to what proportion of them fall outside of that circle. The ratio between the two is going to be proportionate to 4 times pi. Let's look at how we actually do this in our own code, and it's actually not too complicated. And this is some code that I wrote up that's different to the book code. I think last time I checked, the book code had a few issues with it around this challenge with precision and floating point numbers. So I've got a helper function here, which is just a print bits that's used for debugging, and then a main function. So one thing you'll notice in the main function, I'm calling a new function here, srandom. Now, if I look up srandom in the manual, the random function uses a nonlinear additive feedback random number generator, blah, 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 blah. It returns successive pseudo-random numbers in the range from 0 to 2 to the 31 minus 1. So essentially what this function is designed to do is it's designed to give us a pseudo-random number. Now, why is it not actually giving us a real random number? What was your name again?
Michael?
Michael. Why is it not giving us a really random number?
I think because computer cannot do it.
Yeah, what does it mean for a computer to be random? Like, I turn on my computer and I tell the computer, be random, and suddenly out pops a bunch of flowers. I tell it, be random, and a walrus springs to the side. A computer doesn't know what it means to be random and doesn't have a source of randomness in it. Really, what it can do is it can generate a sequence of numbers that to a human eye will look unpredictable. And this is really where my research gets to, is because if you can figure out the algorithm that the computer is using to generate these pseudo-random numbers, and you're using these pseudo-random numbers to generate something important, like a security key, then I can guess what your security key will be and read everything your computer is doing because I was able to guess those random numbers. So there's a whole science to creating random number generators that are what we call secure cryptographic random number generators. And these are random number generators that someone shouldn't be able to detect. You shouldn't, A, be able to tell if it was generated using one of these functions or is actually really random, and you also shouldn't be able to guess what the next random number is just because you've seen the last one. And that's a whole interesting area of research. So I will say, never use these functions when you're doing anything to do with security or even when you really need good randomness, because these numbers are only pseudo-random and only in a very narrow sense. However, to make sure that our function, which is deterministic, doesn't generate the same thing every single time, we're going to use a function srandom instead of just random, which sets an initial seed value for future calls to random. And what this means is it's going to mix something into the function that will just make it seem a little more random. So in this case, if we take the current time, and the current time is going to be a bit different every time you run your program, and mix that into the function, that means every time we run this function, the output's going to be a bit different. Now, the problem with using this for something that needs high security is I can probably guess within reasonable accuracy what time you ran this line of code, and so this is not a safe way of generating random numbers that are used for anything security-wise. This is just good to make sure that it doesn't give you the same random numbers every time you run it, the same random numbers. So then what my function does is I've just got a loop that generates lots of points. I haven't really told it where to stop here. And then I generate the numbers. I deal with some of the nonsense around floating point precision, so you don't have to know how that particular line works, or these ones here. But this is the important part. Then what I do is I calculate the radius of the circle and where the points would fit within it. So I know anything that sits outside a radius of 1 is going to be outside the circle, but still inside the square. And so what I then do is I count the number that have fallen within that radius of 1 and everything that's fallen outside the radius of 1, and then every now and then I just print the value that I've computed so far. And this is the reason why I'm doing it in an infinite loop. I'm just letting it generate as many points as it wants to and report every now and then, and I'll stop it when I want. So let's try it out. And we can see it gets accurate pretty fast. So it's already on 3.141. Let's leave it a minute and see what happens. So we did see that the C standard library has some built-in functions for generating random numbers, but they're not that great. In fact, if you pay close attention, you can find that after a while, the random number generator from C will start to repeat random numbers, and that's probably not that random if you get the same sequence over and over and over. Operating systems also do provide ways to get random numbers, but historically they've also been pretty poor, and that was how I got a PhD, by discovering flaws in random number generator systems and using it to break into large portions of the internet. I think in one instance we got something like 30% of all web servers on the internet were vulnerable to our attack. So modern random number generators that do get used in modern operating systems are better, but still something to keep an eye out for. So there are lots of mathematical and algorithmic challenges for generating numbers from a range. We're not going to go into them, but it's a nice thing to look into a bit later. Now let's revisit our code, and it still hasn't quite gotten there. 3.14159, whoa, almost. We were there for a second. We'll get there eventually. So there are a few other issues with our algorithm like this, with our simulation and approximation algorithms and our random algorithms. There is a chance that if we stop it at a given time, we might get an incorrect result, and it might not terminate. And this particular kind of a randomized algorithm we call a Monte Carlo algorithm, after the famous gambling city of Monte Carlo. So that's one category of randomized algorithm that has these properties where we might get an incorrect result and it might not terminate. But not all randomized or simulated or simulations actually work this way. There is another type of randomized algorithm called a Las Vegas algorithm, which always terminates with a finite runtime. However, you're still not necessarily guaranteed with a Las Vegas algorithm of a correct result. So how would you fix this problem? Michael? It was Michael, right? Yeah. So if you're running a Las Vegas algorithm and it terminates in a fixed time, but you're not sure whether it's returned the right result or not, what might you do?
Can I check the answer? Check the result?
Well, let's assume you don't have an easy way to check the result. What's a clever way to check the result? So you know this algorithm is right, let's say 50% of the time.
Just run it again multiple times.
Okay, and if it's right 50% of the time, that's probably not going to work because you don't know which of the times it was right and which was wrong. What if it's right 80% of the time? You're still on the right track.
Run it again?
Yeah, run it again. So how many times do you reckon we should run this?
As many as we can.
Yeah, as many as we want, and to build up our confidence. And what we can do is if we can bound how likely the algorithm is to give us the correct response, what we can then do is give ourselves a confidence interval on how confident we are given the chance that the algorithm has returned the same answer, say, 10 times in a row or 100 times in a row. And you run it until the level of your level of confidence in the algorithm is appropriate for what you've tried to do. So now on to approximation algorithms. Here we're going to solve a simple version of a problem, even though we know it might not be all the way to the correct version of the problem, but it'll be close enough, within some factor, within some epsilon of the true error, of the true value. So there are places that we really do use these every day as workers in science and technology. So some examples would be numerical integration and solving differential equations, which are things that you might have already turned to do on your calculator or on your computer before. And so these are all using approximation algorithms. And we call the field that studies these kinds of algorithms numerical analysis. So just for a very easy one that you may have already even seen if you've been following along in the textbook, we could do this for approximating the cube root of a number. So here's the Newton-Raphson method for computing a cubed root, or computing approximation to a function. Let's say you have a guess. It doesn't matter how good the guess is, any guess for what the cube root of x is. You can improve your guess by just making this calculation. And this works just because of calculus. You can derive it yourself. It's a very simple approximation method. So let's say you have a guess, q, compute a new guess, q star, and q star is equal to 2 times your prior guess plus x, which was the original number that you wanted to calculate the cube root of, on your guess squared, all of that divided by 3. So we can do this once and get q prime, and then we have a new better guess, and using our new better guess, we can improve on the better guess by doing our process again. So then we get q prime prime, and then we get q prime prime prime, and prime 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 prime, and so on and so forth. And we can also detect when our guesses are not really getting any better. So when they've converged to as close to the answer as they're going to get, or when they're diverging. So we can do either way. So let's look at croot.c, which is a simple implementation that you could even do with much earlier skills from the semester to compute the cube root of a number. Ooh. So who has a guess of what happened there? Michael? Do you have a guess? I heard someone say it. You want to pass it back down to Jack? Pass it forward, over here, down the front.
Integer overflow?
Yeah, that's right. So we've now gone outside I think it's even crashed at this point. It did indeed crash. So we've gone outside the allowable bounds for our integers, and so the math is just messed up. Which tells you a lesson. Number 1, be careful of your integers, and number 2, don't always trust code that I've written. So let's open cuberoot.c. And this code is actually pretty simple. So let's assume that you have a guess. Right? Start with 1 as your guess, and then just repeat however many iterations we've specified, and compute the next guess, and then use next to compute the next guess, and next to compute the next guess, etc., etc. Now, what we've done here is just to make sure that we have bounds, to make sure when our number is getting to the point where we no longer have the precision in our floating point type to actually compute this correctly. And then we can run this for a set number of iterations. So what do we want to calculate the cube root of? Should we start with 9? 9 seems good. Okay, cube root is 2.08. Now let's try something else. Let's try 81. Have a cube root of 4. So you can play around with this and try it with different things that you know the cube root of and see what you get. And it's going to keep asking me to do that until the end of time. Okay. So we've talked a little bit about simulation as well and approximation. And let's actually try this with a real example. So here is one that you'd probably see if you were taking Calculus 2. And if you're taking Calculus, they're going to make you do this awful derivation for how to calculate the motion of the mass given a certain force and the dampening and the Hooke's constant on the spring and all of those. You know, what is it, Toby?
What's even better is the Calculus 2 was taken exactly here with the exactly same figure.
With the exact same figure?
I mean, 2 weeks ago.
2 weeks ago. Okay, so I'm really on a roll here. Now, this is probably from Wikipedia, the figure. Either we could do the Calculus 2 method, which is a lot of work, but you're here because you're all lazy, or at least lazy in a good way. And so what we're going to do is instead, we'll take the equation of motion, and we're going to calculate the derivatives instead, and do this just for small changes in time. And we know that for a small change in time, we don't actually have to solve the entire differential equation. what we can just do is make very small adaptations to the existing motion of the object, calculate the very small change in acceleration, the small change in position, the small change in velocity, and of course our small change in time, which we'll set. And we can choose how long we want this small time to be. The smaller we make the time relative to the other parameters, the better results we're going to get. So if you're using a tiny mass and a very large time, then your results are not going to be accurate at all. This is only going to work when the approximations that we're using actually hold. And if you want more detail about that, either go back to Calc 2 or even better, join me and Rithik in David Caro for some exciting physics. So this is easier than a page of maths, and physicists will use this in all kinds of scenarios too. So we have spring.c. There we go. So I have a graphing function. We're not going to worry too much about that for now, but it's worth taking a look at as an example for future code that you want to do. But the core of our code is going to be in here. So we're going to take in a couple of parameters. We're going to take in the current position of the spring relative to its starting position. So how far how far stretched out is the mass from its resting position, from position 0? What is the mass of the string? What is the time step that we're going to look at? So how frequently are we going to try and calculate these updated values? And then we're going to set its initial velocity to 0 and the initial time to 0. Now, again, because we're a computer science class, the physics is not the important thing here. The important thing is the application once someone has given you these kinds of equations. Not that physics isn't beautiful and exciting and important and should be the love of some of your lives, at least. I see the mathematics students glaring at me. One of them's disappeared. I don't know where she went. She left the room so disgusted. Okay, and then we just have our while loop. And so this is saying repeatedly until we're converging again, until we're no longer getting a significant change in things, keep producing this graph, calculate that, update the variables, calculate the next output. So let's do spring.c. I'm going to compile it, and then in one line you'll see I'm now using this fancy syntax and on the terminal. And what this means is so long as the previous commands have concluded successfully, also run the command on the other side. And it's like a logical AND just being used on the terminal directly. So then I will execute my Spring program with an extension of let's say 1 unit or 1 meter, a mass of 5, could be 5 kilos, and a time step of 0.1. And I'm going to do it like that. Actually, I'll clear this first so we have a nice, clear thing. So we'll have to scroll up to see it, but you can actually see a picture of my mass bouncing around. So here what I'm just computing is the new value for x at each given time step. So remember, x was our extension from the 0 point, and what we're seeing is how it's bouncing onto either side of that 0 point. We get this really pretty picture, and then after some point, it just kind of stops moving. We could also do it with a smaller time step, like that, and there we'll get perhaps a little more accurate of a picture. Now, you might want to play around with this and say, like, what if my mass was 500 relative to 1? And there you'll get something a lot crazier. That's so crazy it's not even going to show in my terminal. Whoa, there we go. My mass is really springing about. Woo. Yeah, this is a very traditional form of animation. And let's cut it off there. Now, just a very quick note about what I did on the terminal is I took the output of the prior command and I sent the output into another command using this pipe symbol. And the command that I sent it into is the less command, which just allows you to view starting from the first page, a page at a time. And that's a very helpful command. So there are a bunch of really cool things you can do with simulation. I'm quite a board game player, and so one thing that I like thinking about is, okay, what would happen if I simulated the board game, and would this be better if I tried to figure out the best solution for the board game by simulation or by one of the other methods? And there's this really fun video that I've got in the slide deck for you to look at later about doing a formal analysis of Monopoly, trying to come up with like mathematical equations that govern it, versus a pure simulation approach to figure out what the best strategy is. Before we get into the break, let's talk about our final strategy for today, and this is optimization. A lot of machine learning and a lot of the natural language processing and chatbots that you've seen are actually, at their core, using optimization algorithms. And the key here is to figure out what is the actual thing that you want to optimize. So in the case of large language models, what we're trying to optimize is to minimize. Optimization and minimization are very, very close, so you can either maximize something or minimize something in an optimization problem. We want to minimize the error in the next word that's predicted. And what do we mean by error? Probably in the case of a real chatbot like ChatGPT, it's our surprise at what the word is. So we want to minimize the human's surprise at the next word. So for example, the kid read from the jellyfish. That's a little surprising. So the kid read from the book. Not very surprising, so that would give us a good score, and our optimization has therefore succeeded because we're not surprised by the output. Now, how do you actually measure that mathematically? Come to one of my talks on AI and natural language processing, and we can give you an overview. But the basic idea here is that we want to find some function, generally, in the world of all possible functions that exist, we want to find a function that computes our desired output as a function of our input. Now, this is totally generic. I haven't told you x here, our input, is just some vector of all the different inputs, right? It's not just a single number, it's a vector of all the things we care about. It could be strings, it could be image data, it could be audio, and our output, I haven't told you what that could be either. It could be a word, it could be a number, it could be anything. But this is the general framework, is that we're trying to find this function, which from our input computes the output. Now, generically, this is hard. There are a lot of possible functions in the world. I mean, I can name like lots of functions off the top of my head. X squared, 2x squared, 3x squared, 2x cubed, 4x squared plus 5, plus log x, plus 24. There are a lot of functions out there. And so naively just trying to enumerate all the functions totally isn't going to work. And so this is an example where generate and test is obviously the wrong solution because it isn't even clear how to explore the space of functions. Instead, what we're going to do, we'll come up with some function that we think might model the desired function reasonably well. So there's a trade-off here between a function that has enough parameters to tweak, such that you think it'll be able to give you a good approximation of the thing you're trying to match, versus a function that it has as few parameters as possible, because for every additional parameter, that's an extra dial that you need to tweak in the right direction. For example, let's say you're trying to approximate a cubic function. A linear line, a linear function, is going to give you a really bad approximation to parts of the cubic, but at other points it's going to be fairly good. What's the advantage of a linear function? You only really have two parameters to play with. You've got the ax plus mx plus c, or ax plus b, whatever it is. You've got that a and the b, and those are the only parameters you have to set. So there are going to be places where it matches the true function really poorly and places where you might actually be able to get it to match really well. And then outside of a certain domain, it's just going to all go to shreds. So obviously, depending on what we think the real function might look like, we'll try and make our model function with those parameters a little bit more complicated. So if we're trying to capture a sine wave, and obviously we can't capture a sine wave over its entire domain using an approximation like that, but let's say we're just trying to do like a couple of ups and downs of the sine wave, and we used, instead of a cubic or a quartic, we use like x to the power of 16. So that's going to give us a whole bunch of twists and turns that we can play around with. And then our goal is to figure out all of the coefficients such that we get a really nice look. And this is essentially all that large language models are doing, just at a much larger scale. So you can imagine there is some function that, given an input that is an English sentence, produces an output of the next sentence that should be output. So you could imagine there is a function that, for a given query in English, tells you what the next line of the book would be were this a book. Now that's obviously a hideously complicated function, so how many parameters do you think we'd need? Jack, maybe? You gotta give it a Gabriel, why not? How many parameters do you think we need to guess what the next sentence of a book will be?
A lot.
A lot? Are we talking hundreds?
Well, I mean, every word in the English dictionary, I guess.
So that doesn't give us necessarily our parameters, that gives us the size of our input space. What's a guess for the number of parameters? Have you heard anything about like how many parameters these very large language models have?
Not really sure.
Billions to trillions is the answer. So instead of like x to the 16, you can imagine like x to the trillion. Now, of course, because computing x to the trillion isn't really a good idea, we're going to have to come up with a better type of way to represent this function, and that you can learn about in one of our exciting AI classes. The fundamental technique that we use a lot of the time to do this, though, is something we call gradient descent. So let's say you're mapping out the error and representing it by the height on a mountain. The higher you are up on a mountain, the higher your error is. And you have all these dials, all these parameters you can tweak, and you need to figure out how you could tweak them. So one thing you can do is you can use calculus to calculate the derivative with respect to each of the parameters. So if I change a small change in this parameter, would that make the error go up or the error go down? That's essentially what derivatives tell us, is which way is a function going as I move along one direction of the function's parameters. So for example, if a function has like a positive derivative, that means if you increase x a little bit, then the function is going to go up. So we want to do this for our parameters and figure out if I make my parameter a little bit higher, will I increase the error or will I decrease the error? And our goal is to find in a multivariable sense, what are the parameters, the parameter changes that we should make such that our error goes down and we kind of climb down from a very high up point of error to a point of error that's a little lower. And this is called gradient descent because to compute the derivative of a multivariable function, we use something called the gradient that those of you taking multivariable calculus may be familiar with. So we compute the gradient, we look for the direction that will reduce our error by the largest amount, and then we tweak our parameters a little bit in that direction. Now, of course, if we moved our parameters a lot in that direction, the gradient will change as the parameter changes a lot. So we can only take small steps and then we recompute the gradient. Okay, now which direction do we go down the mountain? Which direction has the steepest descent? And we keep doing that until we get to the lowest point that we can, which might not be the lowest point on the map. It might just be a temporary valley. If we zoomed out on the world, we would see that this lake is not actually the lowest point on Earth. So we sometimes get stuck, and this is one of the big challenges in machine learning, is figuring out, okay, how do we set our step size and how do we do our steps such that we actually get to the lowest point that we can, rather than just getting stuck in a little temporary, nice, beautiful, but still relatively high up arid lake. So that concludes our discussion of the different strategies, as well as the substantive assessed part of the class. But now I want to take you on a journey a little bit further into the world of computer science, up past second year, up past most of third year, and up until some of graduate school, because I think you might find it fun, and I know all of you are very smart. So we're going to dive into complexity theory, which is the study of how to classify algorithms based on their resource usage and a model of computation. And so who here has heard this last phrase somewhere? Who's been paying attention to the handbook? There's a third year class, Models of Computation, which is essentially aimed at kind of analyzing some of this sort of thing. So when I say a model of computation, what I actually mean is we have to theorize what it means abstractly to be a computer. And this will help us answer questions like, how long does addition take? Because you could imagine a model of a computer that's very abstract and where addition just takes one step. But we know, like deep down in the circuitry, there are no like steps happening. There are things happening on the wire. And depending on how we've built our circuit, addition might take like more than one consistent step. Like obviously, if we're multiplying a super, super, super giant number, it's going to take more than multiplying a super, super small number. And so the abstract model that we build to represent our computer is going to influence how we analyze our algorithms. And that's one of the things that this whole area studies. But I know that's probably a bit heavy for a lot of you. So back to the Sudoku. Rex is suddenly happy again. So we have our Sudoku, And if we remember from earlier in this lecture, we had a whole lot of complicated starting assignments and a whole lot of clauses. And we wanted to answer our decision problem. So is there at least one combination of settings for all our variables where we can set any given variable to be where we can set any variable to be 1 to 0, and our indices will range from 1 to 9. Thank you, Finn. I'll fix up the 0 indexing later. Such that every possible one of our clauses, every one of our constraints is satisfied. Now that's the goal of our what we'll call the Sudoku decision problem. Now, this general version of satisfying clauses is called satisfiability, or SAT for short. So given that we're studying algorithmic complexity and runtimes and that sort of thing, I want to know, if I give you the values of all the variables, how long will it take till you know if it's a valid solution? Jacob, okay, so if I give you the values for every variable, how long will it take you to check if this is a valid Sudoku?
Was that 9 to the power 81?
Say a bit louder.
Was that 9 to the power 81?
So there are 9 to the power of 81 possible combinations. So that's if we checked every combination. But let's say I just give you a solution.
Okay.
How long will it take you to know that it's actually a correct solution?
I'll just need to verify that every number on every line has every number.
Yeah, so we need to verify each of our conditions. So each of our conditions has a number of different clauses. And we computed the number of clauses was like 11-ish thousand. And so we're going to need to run over each of the settings that I gave you at least once, and each of the clauses at least once. And so let's just say that let's upper bound the length of a clause and say the upper bound is 11,000 things, and it's 11,000 literals. And I'm going to use a literal to refer to like the individual little bits of the clause. So that'll be 11,000 is just some constant. Let's make it C. And we can say that there are K of those clauses, and that the number of variables in the solution is also equal to, can just be our n. So we'd get a time complexity to check the solution that's kind of linear-ish. It's linear in the number of clauses and linear in the size of the solution multiplied by some constants that we don't really care about because we're using a computer and the constants for the time being aren't going to be so important. So let's just boil it down to O of n, where n is the length of the string made up of all the clauses, because we need to go through all the clauses and check each of them. And we can do that very, very easily. Like, you know, to check if the result of an AND is one step, to check if the result of an OR is one step. So we just go through and do that. So this runs in what we'll call polynomial time, which means that it is bounded by n to the k for some k. Now, I don't particularly care what the k is. This is just a polynomial. And O of n is obviously less than O of n squared. It's like O of n to the 1 is less than O of n to the n squared. And so because we've got this upper bound, it's also big O of n to the k, which means polynomial time. Now, there's a more precise way of writing it out, but essentially it's just saying that this runs reasonably efficiently. It runs in some power of n. And any problem that is O of n is also O of n to the k, so we're all good. It runs in polynomial time. So what this means for us is we're going to say that SAT belongs in a class of problems that we'll call NP. And what NP is it's all the possible problems for which there exists an algorithm that, given a solution, will tell you if you've got the correct solution in polynomial time. So if I give you a possible solution to a Sudoku, you want to quickly and efficiently check whether it's a valid solution or not. If there is an algorithm that can do this for you, then we call the problem, this Sudoku decision problem, we're going to say that it belongs in NP. One more time, if there is an efficient way to check a solution that you've been given ahead of time, that means the whole problem belongs in NP. Another way of stating this, NP is all the problems that can be checked in polynomial time. It doesn't mean you can generate a solution from scratch, but it means if someone gives you a solution, you can check it. Another thing that we might want to say is we might want to describe Sudoku itself. So Sudoku reduces to SAT because given any instance of a Sudoku, we know a way to turn the Sudoku puzzle into a version of the satisfiability problem. And we did that using the technique we explored before, like set up all of these variables, set up all of these clauses. And setting up those variables and clauses is not itself Sudoku. It's a way of kind of converting the Sudoku problem into another problem. So we call this a reduction. And what this effectively means is if we can solve all of the SAT problems, then we can solve every Sudoku. Because the solution, if we know a general technique to solve any satisfiability problem efficiently, we can just use that trick to solve Sudoku. So the 2 steps would be convert your Sudoku into the satisfiability problem, and then use your efficient algorithm to solve satisfiability to solve the Sudoku, and then just convert it back. Like take the variables and then write them into your Sudoku, and then you have the solution. Rex, do you think this is something you're likely to do next time you are solving puzzles? Think about it, he's not sure. He hasn't enjoyed FOA quite enough. So practically, we can solve a Sudoku SAT. Like if I were to actually do this and do the conversion on my laptop, we could run it in reasonable time. But this is only because a Sudoku is pretty small. Like that many squares is not that large, 10,000 clauses, 11,000 clauses, not that big. We can also show that for any like giant SAT that has all these like multiply chained clauses, you can also reduce it into a version where there are only like 3 individual variables per clause, and then you just have lots and lots more of those. And that's called 3SAT. So that has started to describe our Sudoku problem and our SAT problem. We still don't know many details about it. We don't know how hard SAT is. We know that it's NP, so we know we can easily check it. We don't know if we can easily solve it. So we don't really know if we've made up much ground by converting Sudoku into this. So let's take a look at some other problems and see if we can use those to gain some insights. So here is a map of Australia, and you're giving your 3-year-old this problem. You give them 2 colored crayons, and you say, I want you to draw me a map of Australia such that in the map, no matter which 2 states you look at, they always, if they're touching each other, they also have different colors. So I'll give you a second to think about this. You have 2 different colors. You have orange and purple. Can you draw a map such that... Aditi is shaking her head. Who's got the mic? Who's got the microphone? Okay, pass it back to Aditi. Tell me why you're shaking your head.
Because 2 is too small a number, especially in places where 3 states sort of meet.
So give me an example of one of those states. Do you know Australia?
A little bit. Victoria, New South Wales, and next to that is Southern Australia?
Yeah.
Okay, yeah.
That's exactly right. So there is no way to 2-color a map of Australia such that this property is held. So let's move on. Aditi says, nope. So what about with 3 colors?
Yeah. Maybe.
So what would you do?
If you had red, green, and
So let's go back here. Let's go back there. What would you do? You have a 3rd color now?
Yeah, you would just add the 3rd color to Southern Australia.
Okay, let's add our 3rd color in. Ta-da! Problem solved. A round of applause for Aditi. Solving one of the most difficult problems in our class. But I'm actually kind of not joking. 3 coloring turns out to be a really difficult problem. So my first question for you is this problem in NP? If I give you the solution, can you check it quickly? And how would you do that? Gabriel? Shh. Bad Gabriel.
I'm not too sure, actually.
So do you remember what NP meant?
Sort of. I lost
Say it in your own words.
Well, it was polynomial time, right?
Polynomial time checking a solution or generating a solution?
Checking.
Yeah, checking a solution. So it's if I've given you the solution ahead of time, can you check that it's actually valid? So for this, what would you do to check if the solution is valid? Just run me through the steps.
You would, I guess, just like check if there were any two states of the same color meeting.
So any is hard to do with a computer, but we could do for every state. So
Yeah.
for every state,
You would check if the placement of the color is valid, like in Sudoku.
so close, for any state, check all the states that it touches, and then compare the state of the color that it touches to its own color. If that's violated, if they're the same color, then you know you failed. So we do have an efficient way of checking. And in fact, we found a data structure earlier this semester that can really handle this. So this is a map of Australia. And there you can see I've forgotten which states. What state's down in the purple on the bottom?
Tasmania.
Yeah, that's Tasmania, all alone, sad. So Tasmania, it doesn't matter what color we give it, but for every other state, we have a really efficient way of checking it. We can just go through the graph and check for each of the vertices, for each of the nodes attached to any other node. So for each neighbor, are all the neighboring nodes of a different color. So we can do this in O of n squared pretty easily. That's still polynomial time. But we can also turn this into a SAT problem. And we all love SAT by this point. It's solving Sudoku. It can solve graph 3 coloring. And so what we're going to do, don't leave. Do you have the class after this one?
I'm not sure.
Aw. Don't want to learn computer science? Come back next semester.
Okay.
These people will tell you it's a great class. I hope, right? Yeah. Okay, we have at least a few yeses. Okay, so back from our interlude. Oh, it's so depressing. Back from our interlude. So let's construct a version of satisfiability based off our graph problem. So in this case, let's now have a variable. Let's have 3 variables for every node. So let's say node 0 can be one of 3 colors. It can be color 1, it can be color 2, or it can be color 3. So we have 3 variables. S01, which is if it's the first color, should be set to true. S02, which is if it's the second color, we'll set that to true. And S03, which is if it's the third color, then we'll set it to true. And we want to have a constraint such that only one of these can be true at any given time because each node can only be one color. So this constraint says that node 0 must be at least one of the colors. I don't yet have a constraint up saying that it can be only one of the colors. Then I can write something a little more complicated, and it took me a little while to write this down, but even you could probably do it if you sat down and puzzled it out. And this is that node 0 can't conflict with its connected nodes. So node 0, and if node 0 is true, then it also must be the case that, let me say that again. So let's say that node 0 is color 1. We know that it must be the case that node 1 can't have the setting of 1, and also node 2 can't have the setting of 1. So the way I represent that is I say, if it is the case, or let's say that node 1 is true, then it must be the case that both 1, 1 and 2, 1 are false. Or, so if that clause isn't true, then it could be the case that node 0 is color 2. And if node 0 is color 2, then node 1 can't be color 2 and node 2 can't be color 2. Or we're in the third scenario, where node 0 is color 3, and then node 1 can't be color 3, and then node 2 can't be color 3. Again, to remind you, this is unassessed. This is just kind of fun and interesting. So if we can solve all SAT problems in polynomial time, so again, I haven't told you that we can do this, but let's assume that we can for the minute. If we can solve SAT problems, then we could also solve every graph coloring problem. Because what we do is we do our process to convert the graph coloring problem into the clauses, and then we run that through our SAT solver. So graph coloring, at worst, in the worst case, it's going to only be as hard as SAT. Because if SAT is easy, that would make graph 3 coloring really easy as well. So we could just feed it in and it would tell us, is there a setting of the variables that works out such that the 3 coloring is possible? So showing that we can always convert our problem into a problem of a different type is called doing a reduction. And the steps to do the conversion also have to be doable in polynomial time. So to actually figure out what these clauses are based on the graph also has to be done in polynomial time, because otherwise the total result is in polynomial time. Like if it takes you too long to do the conversion, then you've lost all the benefit from doing the conversion. But if the conversion only takes polynomial time, then you have a polynomial time step plus a polynomial time step. That's still big O of a polynomial. So this gives us some interesting deep connections between our Sudoku problem, our graph coloring problem, and SAT. So in fact, Sudoku is really just a fancier version of graph coloring that's souped up a little. In fact, you can convert any Sudoku into a graph problem, and then you can convert any graph problem into a SAT problem. And now things are getting a little spooky. But we're not quite done. We want to prove that subset sum is also one of these kinds of interesting problems, and we're going to introduce the term NP-complete. So the first thing I'm going to do is we'll show that subset sum, remember this problem before, from a set of integers, can you combine the integers such that you reach your target exactly? This was Blake's backpack problem. First thing we're going to check is the problem NP? Now, who's got the microphone? Still Aditi? Let's get it back to Blake, given that this was his problem. So first question, is subset sum NP? If I give you a set of integers that sum to a given number, can you do that in polynomial time?
Yes.
Okay, tell me the process.
So you go through every item and then add it together so it's related to the amount of items you have.
Do you need to do that through every item that you have? Or if I give you the solution, right? I've told you a subset of items, right? So how many items do we have to sum together?
The amount of items, the subset.
Yeah, the amount of items in the subset, not the amount of total items. So here's our checking algorithm. Given a set of, let's say we have an array that has all our different items in it, and we're told at which indices are the items that make up our solution. So all we do is we go through our array and we sum up the values of each of those items at the right indices. If we're exactly at the target value, return yes, we've found a solution. If not, return no. Now, let's fudge a little. This is still going to be roughly linear time. We can choose to ditch the assumption that all the numbers are small if we want and start to dig into the fact that ultimately addition is going to depend on how large the numbers are, but that's still going to be polynomial time. So is our subset sum problem in NP?
Yes.
It is in NP, and why? Just say once more for me.
Because adding up everything is linear.
And fill in the gaps.
That's a polynomial. Linear is polynomial.
Yep, and what polynomial time is just if someone gives us a solution, can we check that the solution is valid really quickly in polynomial time? So we can check we can check a given solution in O of n to the k time. Remember, we can do it, linear time is a subset of O of n to the k, so we're all good. So subset sum is NP. Now the next step in determining if something is NP complete is figuring out if we can reduce it to another one of these tricky problems. So I'm going to just go ahead and let's assume for the time being that SAT is one of these hard problems, and we'll call it NP hard, because we've seen that so far a bunch of problems can be solved if only we could solve SAT. So let's give it a complexity class. It's in NP, and it's also a hard problem, so we'll call it NP hard. And so now we want to see if we can reduce subset sum also to one of our other NP hard problems. We've got a few of these. We know, well, we don't really have a few of these yet, but we've got our guesses about SAT. So let's say if we can solve every SAT problem using subset sum, then subset sum must be at least as hard as 3SAT. Because if we can prove that 3SAT is really hard, no matter what, and we can use subset sum to solve 3SAT, well, that means that subset sum must be at least as hard as 3SAT is. So this is kind of a reduction the other way. So here is the solution to how to do that. It's another one of these kind of like clever, tricky things. So let's say we have a version of 3SAT, of our satisfiability, and these are the only three clauses that we have over there. We've got three clauses, C1, C2, and C3, and three variables, x, y, and z. And the bar on the top is going to indicate that the value is negated. It is either the case that x is false, or y is true, or z is true. That's our first clause. Our second clause is it is either the case that x is true, or y is not true, or z is true. And clause 3, it is either the case that x is not true, or y is not true, or z is true. Now, you don't have to follow exactly what I said there. The thing that matters is we have 3 clauses, and we want to see, is it possible to find a setting of x, y, and z, so either x is true or not, or z is true or not, or y is true or not? Is it possible to find a combination of those such that all 3 of these work at the same time? And so here's the trick to convert it into subset sum. Pass down to Jack.
Just why is Z never like not true?
Oh, I just picked a given instance of 3-sat.
Right, so I guess it would depend on the
This is just a particular example. Okay. It's like different Sudokus have different clues, and so they might result in different looking clauses. So this is a particular example of a 3-sat problem.
Right, okay. So like
to illustrate the technique.
Yeah, like a different set of conditions.
Yeah,
I guess. And
so just
in
a
this
different
particular
set of
case-
conditions chosen just to illustrate the problem. It's like using a map of America instead of a map of Australia. So we construct a table that looks something like this to start with. And this was like a big result in computer science, so you're not expected to be able to do this kind of thing like just by at the end of studying in class. This is like a big result, how to do this kind of thing. So create a table that looks as follows. Have a column for x, a column for y, a column for z, and then a column for each of the clauses. And in the column for x, put a 1 where for the x is true and a 1 for x is not true. And the y, do it a 1 for x for y is true and a 1 for y is not true. And then the same in the z column. Right now, those columns don't mean anything. And I spot an error. Okay, and then for the clauses, put a 1 wherever that value, if that value appears in the clause. So for clause 1, we can see there's a not x. So there's a not x in the C1 column. Then there's a y, so we put a 1 in the y column. And then there is a z, so we put a 1 in the z. And there's one more trick to it for reasons that will become clear once you know how to make this work. Also put a 1 and a 2 in the first 2 slots beneath that whole structure. And so if you had more clauses, we'd need to make the table longer and longer because we now have this like pattern of 1, 2, 1, 2, 1, 2. And if we had a 4th clause, then there'd be like another 1, 2 down there. And again, there is no clear reason to this other than someone figured out that this is the way to make the problem work. So there's no easy intuition yet. So now what we do is we come up with a target number. And the target number is this number at the bottom. Remember, with subset sum, this is like how much volume we have in our backpack. And the way this works is it's going to be 1 for every one of the variable columns, and is going to be 4 for every one of the clause columns. Now, our goal is to choose rows of this table, such from the first set of rows, which tell us what our variable settings are. If we choose to include row number 1, that's the same as saying we are picking x to be true. If we pick row number 2, that's going to be the same as saying we pick x not to be true. Row number 3 is we pick y to be true, etc., etc. So what you can do is you can write down the rows as a set of numbers that correspond to the 1s and 0s in the table. So choosing one of x or not x is equivalent to choosing one of those first 2 rows, which gives us these 2 numbers. You can do the same thing for y and the same thing for z. And then you can finish off with any of the rows at the bottom of the table that you like. So we have these rows at the bottom of the table, these w's, and you can pick any combination of them that you like, and then your goal is to get to this target number. What this target number means is the first 3 ones correspond to picking an exclusive setting for each variable. So either the variable is true or not true. So let's look at x and not x. If we were to pick both of these numbers and sum them together, we would have a 2 in that very first column, which means that we wouldn't have reached our target exactly, because our target starts with a 1. Our target starting with a 1 means we can only pick one of x or not x. Likewise, the second one in our target means we can only pick one of y or not y. And if you add this up, you'll see that these first 3 ones impose the constraint that that the variable can either be true or not true. You can't have true and not true at the same time. And then these 3 4s are ensuring that each clause is satisfied. And you can do similar workings to show that the only way to get a 4 in each column is if you've successfully satisfied a clause. And so now what we've essentially done, we've done this complicated, tricky thing, and don't worry if you haven't quite gotten it. It took me a while this morning to work through this one. This is the first time I'm showing it ever in the class. What this means is we have successfully found a way to convert any 3-sat problem into a subset sum problem, which means if we find a solution to subset sum, then we have found a solution to every 3-sat problem. And if we believe that 3-sat is indeed really, really hard, that means that subset sum must also be really, really hard. So there's this deep link between them. In fact, we can start coming up with a whole bunch of these clever tricks for a whole bunch of clever problems and show that all of them are ultimately linked. If we can solve subset sum, then we can solve sat, and you can do a proof both ways. So you can show that you can convert sats into subset sums and subset sums into sats, etc., etc. Now, we don't have two-way proofs for every possible problem, and there are only certain problems that we've discovered that are actually in this hard category. And so what we've done by first showing that subset sum is NP, and that there's a reduction from an existing hard problem to subset sum, it's going to fall into this category that we call NP complete, where both of these conditions are true. We can check it really efficiently, but we think it's really hard to find solutions to. So we know if you can solve the hardest of all the problems in that graph quickly in polynomial time, then you can solve all of them in polynomial time. So now we move to one of the crowning achievements of computer science. And this is the Cook-Levin theorem. And this says that if SAT is solvable in polynomial time, then all problems in NP can be solved in polynomial time, and we're going to call this property NP completeness. So it's this property that solving one of them leads to solving all of them. And what they essentially showed is right up until now we were conjecturing in this class that SAT was hard to solve. And what the Cook-Levin theorem shows is it actually is. So now we get this nice picture of what all the problems in the world look like. So we have NP hard problems are all the problems that are at least as hard as the hardest problems in NP. Then we have all the problems that you can check efficiently, and that's all the problems in NP over here. And then we have the NP complete problems. So this is problems for which there are both things true. We can check them quickly, but solving them is really, really hard. Generating that solution is hard, but checking a solution once you've found it is really, really fast. And if you go up the graph, as you go up, the problems get harder and harder and harder. So is SAT indeed solvable in polynomial time is really our big question at the end of the day. Is it the case that there exists in the world an efficient way to solve SAT? If there's an efficient way to solve SAT, then there's an efficient way to solve all our other problems. And so this produces a picture like this. There are two worlds that are possible. Either all problems have a polynomial time algorithm to generate the solution, or there are some problems that are easily checkable but hard to solve. And we don't know which of these two worlds we live in. Is it the case that there's really a polynomial time algorithm that could solve all the other problems? Or is it the case that there isn't? And this problem is known as P. Does P equal NP or not? Or just P equals NP or P doesn't equal NP? We don't know which of these is true. And in fact, if you solve this, there is a $1 million USD prize. Now, do I encourage you to go out and try solving this? So every year there are a whole bunch of people who have claimed to have solved this problem. There is a whole page online that a well-known computer scientist put together discussing the problem. And pretty much every couple of months without fail, some crank on the internet puts out another proof claiming to have solved the problem. Now, if it did turn out that P was equal to NP, if there is a fast algorithm to solve this, all of these other problems would be easy as well. So speech recognition would be easy, cryptography wouldn't work anymore. We would be able to have a computer solve all of mathematics for us. You wouldn't need humans to do mathematical proofs because a computer could do the mathematical proofs easily. Because you can show that the problem of generating proofs also reduces to one of these problems. There are a whole bunch of things that would become really, really easy were P equal to NP. So there are some people have thought about like making movies about what happens if it turns out that P equals into NP. Now you might say, well, we do a bunch of things. We do speech recognition. So it turns out that we can solve like particular instances of these, just like we could solve graph 3 coloring on the map of Australia. We can solve certain size instances. There might be some instances that are easier to solve than others, and we can actually do this. We can sometimes do approximations. We're not doomed. But if it does turn out that P equals NP, then the world would be an entirely different place. There would be no special value in creativity, because essentially we could program creativity in a bunch of ways. And there would be no gap between your ability to check a solution and create a solution. So we all know a bunch of problems where that we find it easy to check, but where we find it hard to come up with a solution in the first place. And if P equals NP, there is no fundamental gap between these two. And with that, that's the end of Foundations of Algorithms. I'll see you all tomorrow for a little more fun stuff, but I hope you've enjoyed.